Hello class, welcome to this video on the Chapter 1 AP Statistics Practice Test. So we're going to break this into, we're going to review Unit 1, we're going to break it into two videos. This will be Chapter 1, and then we'll do another video for Chapter 2. So the first question says, an airline records data on several variables for each of its flights. Model of plane, amount of fuel used, time in flight, number of passengers, and whether the flight arrived on time. The number and type of variables recorded are, so we need to write down the variables. So we'll go ahead and do, we'll have categorical on one side. And we'll do quantitative. And if it's quantitative, is it quantitative discrete or is it quantitative to continuous? Okay, so if we look at the model of plane, the model of plane is going to be categorical. The amount of fuel used, that's going to be quantitative, but since it's talking about the amount of fuel, that could vary into decimals, multiple amounts. So we're going to use that, we're going to put that under continuous. We have the time in flight. Again, time, we're going to, that's going to be a continuous quantitative variable. So time in flight. Then we have the number of passengers. That's accountable, and it's whole numbers. So it's very specific numbers. So that's going to be discrete. All right, and then we have whether the flight arrived on time. So whether flight arrived on time. That's going to be categorical because that's going to be a yes or no question. So here we have two categoricals and we have three quantitative, but two of them are continuous. So the answer here is C. Okay, so number 2, the students in Mr. Tyson's high school statistics class were recently asked if they would prefer a pasta party, pizza party, or donut party. And the following bar graph displays the data. So they're saying, what is wrong with this graph? So why is it misleading? Well, a couple things you want to look for in graphs. So if they ask you why the graph is misleading, the two main reasons that we're looking for are, well, the y-axis, like the y-axis doesn't start at 0. Or the other reason would be like if you have a histogram or a pictogram. So you want to beware pictograms. You don't want to have pictures represented as in your graph. So here we're looking at the fact that we start at 4 instead of 0. And the reason that's a problem is because, well, now the bars don't look as big. So like the donut bar does not look as big because we skipped straight to 4. And so what that does is that it makes it so if donut is 5, and pasta is 18, well then 5 is a little bit more than, or 18 is a little bit more than 3 times greater than 5, right? 3 times 5 is 15, so 3 and then some extra, right? But if you look at the donut bar, here it looks like it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, at least 10 or 11 times smaller, right? Or the pasta looks 10 or 11 times smaller, bigger than the donut. So there's so it kind of fools your eye into thinking that the pasta is way greater when it's not. So here the answer is D. So 1.3, 40 students took a stats test worth 50 points. The dot plot displays the data, and they're looking for the third quartile. So the third quartile, first we need to find the median, and then once we find the median, we can go ahead and find the median of the lower half and the median of the upper half. So it says we have 40 students. That means the halfway mark has to be dividing 20 below, 20 above, right? So we're looking for 20 dots here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So this is the 20th dot. So it's got to be here so that there's 20 on the left and 20 on the right. So this is the median, otherwise known as the second quartile. And then we need to find the third quartile, which is the median of the upper half of the data. So now we need to find the median of the upper half. Now there's 20 dots here. So that means at the 10 mark, we'll cut it in half basically. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means that we're going to need to cut it here. And so the third quartile looks to be 44 for the so this is the third quartile. Looks to be about 44. Okay, so the answer is B. All right. So it says questions 1.4, 4 and 6 refer to the following setting. Realtors collect data in order to serve their clients more effectively. In a recent week, data on age of all homes sold in a particular area were collected and displayed in this histogram. Okay. So which of the following could be the median age? So we're looking for the median. Remember, the median is separates the 50%, right? From the bottom 50% from the lower 50, that's in the top 50%. And so what we need to do is we know that, well, from here it says that we don't know how many homes there are they don't actually tell us, but we can figure it out from the data. All right, so here we have, so it looks like this is 7, then we have 8, then this bar is 9, this bar is 7, we have 6, 3, 4, 2, and then 2 1s, we got 3, and this bar is 1. So we need to add up those numbers to figure out our total. So go ahead and do that here. Okay, so we got 7 plus 8 plus 9 plus 7 plus 6 plus 3 plus 4, so on and so forth. And that's 52. So we have 52 homes. And so half of that, right? So we have 52 divided by 2. Half of that is 26. So we need to look for around the 26 mark, right? And that's where we know about half. We're at the halfway mark. Okay, so if we do, for example, 7 plus 8 plus 9, that gives us 24. So that means we right after the 9 bar, looks like we hit the median. So after this 9, once we hit the 7 bar, we start hitting the median. So this is going to be where roughly the 50% mark is. So that means if I look at the bar, it looks to be in the 17.5 to 25 range, right? Oh, I'm sorry. I said 17.5. This is 20, not 17.5. Sorry about that. So this is 20. So from 20 to 25, right? Basically, right there. That's 20 right there. It's kind of hard to see my writing. That's 20. So it's got to be between 20 and 25. So we're going to pick a choice that matches that. So not 19. So it looks like the answer has to be B. So it's approximately, 24 years could be the median. All right. So now 1.5, which of the following is most likely true? So we're looking to see if the mean is greater than the median, and so far, so on and so forth. So if I look at the distribution, the distribution appears to be skewed right? So since it appears to be skewed right, that means that the median, we know that we have established already that the median is here. That's the median, which means that the mean is going to be pulled to the right. Okay, so if it's skewed to the right, the mean is going to be pulled in the direction of the long tail. So the mean might be somewhere here, okay? And therefore the mean is likely to be greater than the median. So here we have mean is greater than the median. So it's got to be, so far we're based on that, we have A and C, right? So now let's look at the range versus the IQR. Okay, so to answer this question, you have to consider it the same way you would treat the mean and the median. Okay, so the mean is considered a non-resistant statistic, right? Which means that it does not do very well at resisting outliers. So if you got an outlier in the mix, then it's going to vary the mean by a lot. Same thing with the range. Okay, so the mean and range are both non-resistant. However, the median is resistant, right? And so is the IQR. The IQR is also resistant. Because the IQR, remember, if you recall, the IQR looks at the center of the data. This is like the IQR, right? It's in the center 50% of the data. So if I toss in an outlier here or on the left side, on the left or the right side, it's not going to really affect IQR. So therefore, we expect that the range, because we have outliers here on the right side, like this one here, for example, that's going to affect the range and increase it. Okay, so therefore we would expect that similarly, the range would also be greater than the IQR. So the answer is C. All right, so now let's look at 6. The standard deviation of the distribution of house age is about 16 years. Interpret this value. All right, so remember that the standard deviation, when you calculate the standard deviation, the formula for the standard deviation is the square root of the sum of the values from the distance of the values from the mean squared divided by n minus 1. And so what that does is it takes each data value, let's say x1, x2, x3, and x4. Let's say the average is x bar, right? Then it takes, let me do this in red. So let's say the average is here, x bar. It takes each data value and calculates the distance from that data value from the mean, right? So it's going to be the data value minus x bar. Same thing for this guy. It's going to take that value minus the x bar. And then what you do is you square these deviations, you add them together, and then you divide by how many you have. And then, of course, top it off with the square root, of course, and you do this for all of them. So what you're doing is you're finding the typical distance from the mean. So the typical distance from the mean is the standard deviation, right? So it's the average distance from the mean, okay? So that's how we're going to interpret it. All right, so interpret the value. So for this example, let's see, the age of all houses is within 16 years of the mean. No, that's not correct. The gap between the youngest and the oldest house is 16 years. Nope, that's the range. The age of all the houses in the sample is 16 years from the mean. No, the age, that's not true for all the ages, right? The gap between the first quartile and the third quartile is 16 years. No, that's the IQR. Remember, the IQR is third quartile minus first quartile. The age of the gaps in the sample typically varies. So on average, it varies by about 16 years from the mean. That's what we're looking for. So the answer is E, all right? Okay, so 1.7, it says the mean salary of all female workers at a company is 35 grand. The mean salary of all male workers at the company is 41 grand. What must be true about the mean salary of all workers in the company? Okay, so what can we infer from this information? Can we infer, for example, that if I did 35,000 plus 41,000 and I divided that by 2, can I infer that my average is going to be 38,000. Is that necessarily going to be true? The answer is no. That this is only true if there were 50% female and 50% male in the company, right? If that were true, then you would have 50% of, you would have 0.5 or, yeah. So you would have 0.5 of 35,000 plus 0.5 of 41,000. Then notice that is equivalent to that statement there, right? The statement on the left. 0.5 is the same thing as 1/2. So this is only true if you have 50% female, 50% male. However, that's likely not going to be true. This says what must be true. So therefore, this cannot be the answer. A cannot be the answer. All right. Can it be larger than the median salary? Well, again, we don't really know what the median salary is because we don't know how many female or male workers are there, right? So that's going to make a difference because we would have to know the salaries of all the females, the salaries of all the different males, and we would have to sort them from smallest to largest to find the median salary, right? So it may or may not be true that it's larger than the median salary. Could it be any number between 35 grand and 41 grand? The answer is yes, right? So for example, if we had no males, then the mean salary is simply 35,000. If we had 10% males, then the median salary is likely to be close to 35,000, maybe 36,000 or whatever if you do the calculation. If there's a lot of males, then the mean salary is going to be closer to 41,000. So it's a number between those, okay? So this is going to be true. All right, and this is known as a weighted average, okay? So a weighted mean. So the weighted average is the weight times the value plus the weight times the value divided by the weights, okay? So you might be familiar with this if you're talking about weighted GPA, right? Or weighted grades. So things like that. So like in this example, if there were, for example, 10% female, or well, let's say 60% female, 40% male, then it would be 0.60 times 35 grand for the female salary, and then 40% are male times 41 grand for the salary. Then you would divide that by 0.60 plus 0.40, but we know this is simply 1, so it doesn't really do anything, so we can ignore it. And then you can calculate the salary here. And in this case, we can do it just to give you an example of how this works. And the salary will be 37,400. Okay, so if there were 40% males, 60% females. Okay, and so that gives you an idea. All right, so let's look at number 8 and 9. It says, questions 8 and 9 refer to the following setting. A survey was designed to study how business operations vary by size. Companies were classified as small, medium, or large. Questionnaires were sent to 200 randomly selected businesses of each size. Because not all questionnaires were returned, they decided to investigate the relationship between the response rate and the size of the business. The data are given in the following two-way table. All right. Okay, so what percent of all small companies receiving questionnaires responded? So we want to look for, this is a conditional probability, right? So they're looking for a conditional relative frequency here. What percent of all small companies? So we're looking for all the small companies. So of the small companies, there are 200 of them. Of those 200, how many responded? 125. Okay, so it's going to be 125 out of 200. Which is the same thing as 62.5 out of 100. So that's 62.5% if you convert that to a percent. So the answer is E. All right, so let's look at number 9. Which of the following conclusions seems to be supported by the data? Okay, so what we're gonna do is we're gonna calculate the conditional distribution. So let's go ahead and calculate the conditional distribution of response for each business size. Okay, that's what we're going to do. We're going to calculate the conditional distribution of response for each business size, so, or business type or whatever. So here we got the small business, 62.5% response rate. So that's for yes, this is for no. So then if we calculate this, it's going to be 37.5%. Okay, this is for small business size. So I'm going to put small here. I'm actually going to do this. I'm going to move this over. Oops. Let's try to move this over here, just so that we have more space. All right, so there's that. And then we're going to do medium. All right, so remember that these add up to 100, so that's why I found that quickly. All right, so the median, total these. So if I total those, I also get 200. If I total these, I get 200 as well. So this actually makes it nice. Makes it really nice. So we got 81 out of 200 responded. So that's going to be 40.5%. Here, this is going to be 59.5% did not respond. And lastly, we have large business. And it was 40 out of 200, which is 20%. And this is 80%. Okay, so this is the conditional distribution of response for each business size. And so you can see that you got the higher response rate for the small business, right? Compared to the large business. So there seems to be an association between the business size and the response rate. So as the business size increases, it looks like the response rate decreases. You can see that association based off of the data. And that kind of makes sense. If you're a large business, you're less likely to, it makes sense that they're less likely to respond, to questionnaires and things like that. Maybe because they're so big and, it's hard to handle that sort of thing if you're a large business. So that's perhaps maybe the reasoning, but we're not sure. Okay. So which of the following conclusions seem to be supported? There are more small companies than large companies. That is actually not true. Small companies appear to have a higher response rate than medium or big companies. We can definitely conclude that. Exactly the same number of companies responded as didn't respond. And that's not true because we can see that the numbers that responded were different. Overall, more than half of companies responded to the survey. Is that true? Is this 50% here? Well, it's likely to not be because if you look at the ones that did not respond, a couple of them are already over 100. So that's likely not to be true, right? If you just quickly look at that, that's not going to be true. If we combine the medium, and large companies, then their response rate would be equal to that of the small companies. Let's see, medium and large companies. If I add these up, I get 121, which is definitely not as big as the small companies. All right, so let's look at number 10. An experiment was conducted to investigate the effect of a new weed killer to prevent weed growth in onion crops. The two chemicals were used, the standard weed killer and the new chemical. Both chemicals were tested at high and low concentrations on 50 test plots. The percent of weeds that grew in each plot was recorded. Here are some box plots of the results. So we got comparative box plots here. So which of the following is not a correct statement about the results of this experiment? Okay, so that means a lot of these are correct, and we want to pick the one that's not correct. So let's look at A. At both high and low concentrations, the new chemical results in better weed control than the standard weed killer. So we got here high concentration in the standard. It says the new chemical is better weed control. So let's see if that's true. So N is the new chemical. So looking at N high concentration versus versus the standard high concentration. So if I look at the new weed killer, there seems to be a lot of variability. On the one hand, you get some outliers that are very good, or that are not very good, that are very high, right? So that are very high, right? So it looks like the variability of the new chemical is very high variability, which is not a good thing. That means it's very inconsistent. Yes, it has some very good percentages there, right, of weeds that grow. You know, if you're talking about not wanting weeds to grow, right, then that's pretty low. You want that percentage to be low. But on the other hand, it has some really high outliers. So that doesn't seem to be very good. So yeah, we don't have some very good results there. However, we do have, if we look at the data overall, it does seem, even though that even though there's inconsistency here, right? We can clearly see that there's inconsistency here. Overall, it still seems to be better in the sense, because if we look at this, this represents 50% of the data, right? That's the median. So to the left of that is 50%. So that means that 50% of the samples for this chemical, 50% actually were on the low side, right? We're on that side. And what percent of those were, so 50% were low, 50% were high. If I compare this to that, right? Well, then that means maybe 40% or whatever were actually below that. So that's actually pretty substantial, right? So definitely this part right here is definitely an improvement over the standard killer, despite the fact that, you have inconsistency here. But if you look at this here, it actually is interesting because most of the data seems to suggest to be lower than the maximum on this. So at the very least, you have most of the high chemical or the new chemical being at this maximum or lower. Okay, so therefore, this actually is better than the standard chemical, although the variability is still high, and so it may not be as consistent as we want, but it does result in better weed control. So there's that. So we're going to say that this is a correct statement based off of what we're seeing there, and therefore we are not going to choose this as an answer. Now let's look at, actually we need to compare the low concentration, so let's do that real quick. Again, the low concentration looks like 50% are actually, below what this standard chemical has. And so therefore, it does result in better performance. So now let's look at part B. For both chemicals, a smaller percentage of weeds typically grew at higher concentrations than at lower concentrations. A small percentage of weeds. Okay, so what we're doing is comparing high with low. So if I compare the high here with the low here, it looks to be that most of the weeds are on the low end here, right? From 35 below. Whereas here on the low concentration, it was at the maybe 38 mark and below. So it does seem to be that a lot of the weeds are less than they would be for the low concentration here. Now, if I compare high with low for the standard one, definitely there's high percentage of weeds here. There's very low for the standard one, right? The lower percentages. So I would say that is a correct assessment. So for part C, the results for the standard weed killer are less variable than those for the new chemical. So standard weed killer is less variable. So that means we're saying it's less spread out. That does seem to be the case. This is a small spread. The IQR, which is the distance from here to here, that's the IQR, is very small here compared to the normal one or the new one. Okay, so the newer one has higher variability than the standard one. So that seems to be true. All right, so that is true. High and low concentrations of either chemical have approximately the same effects on weed growth. Okay, and we know that that's clearly incorrect, so I'm going to circle that. That's incorrect because that contradicts what we said about part B. Remember in part B we said that there's smaller percentage of weeds at higher concentrations. So that indicates that the higher concentration is more effective than the lower concentration. So it has to be D. Okay. All right, so now we're looking at the free response. So it says, show all your work, clear, indicate the methods you use because you'll be graded on the correctness of your methods as well as in accuracy and completeness. So we're going to be showing our work, constructing, here it looks like we're constructing a histogram. So it says you're interested in how many contacts older adults have in their smartphones. Here are data on the number of contacts for a random sample of 30 elderly adults with smartphones in a large city. So we're going to construct a histogram. Okay, so we're going to show you how to construct a histogram. So we've done this before, but let's just kind of remind you of how it works. So first we need to select our number of classes. So number of classes, usually you want to choose, between 5 and 10. So let's go ahead and choose 8 classes, just to give you some practice on how to set them up. The more classes you have, then you'd have to set up more, which gives you more practice. So we'll do 8 classes, but again, you could choose from 5 to 10 for this. But let's do 8. Then you need to calculate your class width. So your class width is your range divided, your maximum minus minimum, divided by the number of classes. So you're going to take your largest number, which I think these are sorted already, so that's very nice. So the largest is 151, the smallest is 7. So 151 minus 7 divided by 8 classes. So that turns out to be, so we'll go ahead and do that here. 151 minus 7, 144 divided by 8 is 18. All right. So remember, we have to bump this number up. Okay, so if we want to start at 7, right? If we want to start at 7, then we have to bump that number up, okay? So I'm going to bump that number up to 19. All right? So again, I'm going to bump that number up to 19. So always bump that number up regardless of whether it's a decimal or a whole number. This gives you enough wiggle room so you can do your, so you can make your graph and have enough space. Okay, so let's go ahead and do our frequency table. So we have our class, we have our frequency. So we're going to start with our smallest number. So we got from 7 to less than. Now we're going to add our class width to that. So 7 plus 19, right, is 26. Okay, so then we're going to keep doing that. We got 26 to less than. Now we're going to add our class width, 26 plus 19. So that's 45. So 45 plus 19 is 64. And rinse and repeat. You want to keep doing this until you get to 8 classes in total. All right, here we go. We got 8 classes, and looks like we have enough space, plenty of space here, and to include, to have our maximum in our last class. So that's nice. All right, so how many numbers do we have from 7 to 25? Because 25 is less than 26. Okay, so from 7 to 25, so that's 1, 2, 3. We do not include 25 because we got, or actually, no, we include 25. I'm sorry. We wouldn't include 26, right, in that first row, but we could include 25. That's 1, 2, 3, 4, 5. That's 5 numbers. So this is fine. Now 26 to 44, right? So 1, 2, 3, 4, 5, 6, 7. We do not include the 44. Or no, we include the 44. I'm sorry. I keep saying that. We don't include this 45. So don't include that. All right. So let's see. So how many numbers was that? We got 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we got 8 here. And now we got 45 to 63. So now we can include this 45. So 1, 2, 3, 4, 5, 6, 7, and that's it, 7. 64 to 82. 1, 2, 3, 4, 5. And 83 to 101. 102 to 120. There's no 102s, no 120s. 121 to 139. And then last one is 151. All right, so there's our table. Now we can construct a histogram. We have our frequency on the y-axis. And we're going to go up to 8. Then we have our number of contacts here. Okay, so we got here, we're going to use our class numbers, our class limits. Okay, and then we can start drawing our bars here. So we got from 7 to 26, we have a bar of height 5. Then we got the next one is bar of height 8. Then 7. Then 5 again. 3. 0. 1. And 1. Okay, so there we go. There's our histogram. So we constructed our histogram. Now, are there any outliers here? So we're going to see if there are any outliers. Justify your answer. Okay, so let's look at the data here. I mean, we have a bunch of numbers here. The data, original data, as well. Okay, so let's go ahead and look at, and let's use the 1.5 IQR rule. So this was for part A, right? So part B. All right, I'm going to delete this here so I can look at the data. Okay, so for part B, we're going to use the 1.5 IQR rule. So we need to find the median, work our way towards the center. So this is data on 30 elderly adults. So we're going to look for the 15 mark, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So right here, this marks the 15th one. So that means that the first quartile is here, is between the 45 and the 46. Or the second quartile, I'm sorry. So this is the second quartile, or the median, same thing. So I'm going to say the second quartile is here. And so it separates the left half from the top half, right? Oops, I put it on the wrong side. Sorry, it's on this side. There you go. So 15 on the left of that and 15 to the right of that. So sorry about that. So now we have 15 on the left. And so we got to work our way towards the middle. So we got 1, 2, 1, 2. I'm just going to cross them out instead. We got 1, 2, 1, 2, 2, 1, 2, 1, 2, 1, 2. So this is going to be our first quartile. Okay, so we got our first quartile. Now we're gonna get a third quartile. 1, 2, 1, 2, 1. Okay, this is our third quartile. Okay, all right. So now we're going to find our interquartile range. So our interquartile range, our IQR for short, is the third quartile minus the first quartile, which is 47. All right, so now we're going to multiply that by 1.5 for the 1.5 IQR rule. So let's see, 1.5 times 47, that's 70.5. Okay, so we got 70.5. So now, to get the lower outlier, it has to be less than the first quartile minus 70.5. The first quartile we established is 30. So it's 30 minus 70.5 is negative 40.5. Okay. Now our high outlier has to be greater than the third quartile plus that. 77 plus the 70.5, which is 147.5. Okay, so if there are any numbers greater than 147.5 or less than negative 40.5, they're considered outliers. We do seem to have an outlier because it appears that 151 is an outlier. So 151 is greater than 147.5. Therefore, 151 is a high outlier. Okay, so we do have an outlier and we justified why that's the case. Would it be better to use the mean and standard deviation or the median and IQR to describe the center and variability? Well, if you look at the shape of the distribution, it does appear to be skewed right. And we've established that there's an outlier here, right? We've calculated that outlier. And so that's telling you that if it's skewed with outliers or just skewed, we are going to use, since it's skewed, we are using the the median and the IQR. Okay, so for symmetric distributions, you can use the mean and standard deviation. For median and IQR, for skewed distributions with outliers, use the median and the IQR to describe the center and variability. Okay, so it would be better to use the median and IQR because the distribution is skewed and has an outlier. All right, so there we go. Here, in this case, I'm just going to put it's skewed to the right. I forgot to put that there, but if it's skewed in general, you're going to be using median and IQR, but I just want to be more specific. In this case, we have a high outlier and we have a skewness to the right. Okay. All right, so here we go. So we got a study among the Pima Indians of Arizona investigated the relationship between a mother's diabetic status and the number of birth defects in her children. The results appear in the two-way table. All right. So it says so we have our data, our two-way table for that. What proportion of the women in the study had a child with one or more defects? Okay, so of the women in the study had a child with one or more defects. Okay. Okay, so first off, we're going to need to find the totals. Okay, so let's go ahead and just do the totals here. So here we have 785. Here we have 375. Here we have 47 for the total here. Okay, so for the total here, we have 754 plus 362 plus 38. So it's 1154. We got 9 plus 13 is 22. And so that's going to be 53. So if I add those together, I get 1207. Okay, so there's 1,207 mothers in the study, or women in the study in total. And out of those women, it appears that 53 had one or more babies with one or more defects. So here we have 53 out of 1,207. Okay, so about 0.044. All right, so part B. What percent of the women in the study were diabetic or pre-diabetic and had a child with one or more defects? So we're doing diabetic or pre-diabetic, so it could be either one of these, and one or more defects. So that means we're looking at these, one or more defects and pre-diabetic or diabetic. So that's going to be 22. So I mean it's going to be 13 plus 9, which is 22 out of 1,207, which is 0.018. Okay, so now part C, it says make a segmented bar graph to display the distribution of the number of birth defects for the women with each of the 3 diabetic statuses. Okay, so very important to understand this, that when you're making a segmented bar graph, what goes on the x-axis is the explanatory variable. Okay, so when you do the segmented bar graph, you have the x-axis and the y-axis. The x-axis is the explanatory variable. The y-axis is the response, or in this case, when you do your key, right, with the different statuses or whatever, that's going to be your response variable. All right, so that's very important. So in this case, what is my explanatory variable? Well, my explanatory variable is diabetic status, because that would help explain why, or predict why there's a certain number of defects. Okay, so we're trying to see, okay, well, if the diabetic status gets worse, it appears that maybe there'll be more defects. That is the potential implication there, but we can see it in the data by making the bar graph. So here we're going to do the conditional distribution of the number, the distribution of the number of birth defects for each of the 3 statuses. So we're going to do just that. So first, let's do the conditional distribution. So here we got number of birth defects. Okay, so I'm going to put none, 1 or more. We got non-diabetic, pre-diabetic, and then diabetic, right? Just to kind of shorten it. All right, so here we got, out of the non-diabetics, which were 785, right? 785. So out of these guys, I'm just going to show my work for that. So out of the non-diabetics, it appears that 754 had no defects, right? No defects reported. Okay, so let's see what that is as a percent. So 754 divided by 785, so that's 96.1%. So we're just going to round it. Okay, and then this one's going to be 3.9% for that. All right, so out of the 375 pre-diabetics, 362 had no defects. So so this one here out of 365, 362 had none. So 99 point, hold on. Sorry, not 365, 375. Let's change that. So 96.5%. And then so this is going to be 3.5% here. All right, and then this is D for diabetic. So for that, out of the 47 diabetics, 38 had pregnancies with no defects reported. That's going to be this one here. So that's 80.9%. So it's going to be about 19.1%. All right, so it does look like as the diabetic status gets worse, right, it appears that the number of defects increases. So you got one or more defects increases. All right, and increases drastically from non-diabetic or pre-diabetic to diabetic. So that's something to keep in mind. Okay, so here we go. So we're going to make a segmented bar chart for this. See what we get. All right, so let's do the segmented bar chart over here. So here we got percent, and then here we got the diabetic status. So here we got non-diabetic. We had pre-diabetic. I'm going to move this down just so I have more room. Yeah, pre-diabetic. And we had diabetic. All right, and we have two different things going on. Either they have no defects or they had one or more defects. So we're going to do a key. So we're going to say if we fill it up, if we shade it, it's 1 plus defects. If we don't, then there's none. No defects. All right. Okay, so now we can do it. So 96.1% no defects for non-diabetic. So let's go ahead and go by 20s. Okay, so non-diabetic 96.1. So it's going to be pretty close to here. This is 90 here. That's 95. So it's going to be like around there, 96.1-ish. Pretty close to that. Okay, so that was no birth defects, and then from here to here was the defect, so that's shaded. And then for pre-diabetic, it's pretty similar, 96.5 and then 3.5, so it's going to be very similar. And then diabetic is when things start to change. So once you get to that diabetic state, it appears to influence things immensely. So here we got around 80%. Try that again. Sorry. Trying to make sure that lines up. All right, and then get this up to 100. All right, so you can see there's a drastic difference when you're looking at comparing the first two to the third group. Okay. Actually, I should bring this down a little bit more. So I'm going to bring this down a little bit more here. There you go. So you can kind of see the difference there. So there you go. So that's my segmented bar graph. Now we're going to describe the nature of the association. So like how we were kind of alluding to, there definitely seems to be an association. So we're going to say for part D, there is an association between diabetic status and the number of birth defects. Okay, so then we're going to explain a little bit more. So we're going to say that non-diabetics and pre-diabetics have similar rates of birth defects. But those with diabetes tend to have higher rate of birth defects. Okay. All right. So there's our little explanation there. So now let's take a look at the next. This should be the last question here, so we can wrap it up. Okay, actually there's a couple more. So we have a stem plot and we have a box plot. Okay, so back-to-back stem plot shows the lifetimes of several brand X and brand Y batteries. So what is the longest that any battery lasted? So we're gonna use this to compare. Okay, so remember it says that if we have, for example, 4/2, that represents a battery that's from 420 to 429 hours of battery life. Okay, so that's how we want to interpret it. So here the longest battery, it says 5/5, right? So 5/5 means 550 to 559 hours. So that seems to be the longest. Okay, so the longest battery life is between, it's from 550 to 559 hours. All right, part B, give a reason why. Give a reason someone might prefer a brand X battery. Okay, all right, so let's look at brand X. So brand X seems to be that, if you compare that to brand Y has one that's like 170 to 179 hours of battery life. That's pretty low. But if you look at brand X, the lowest that it has, it's 300 hours, 300 to 309 hours, right? And then, so it has a higher minimum value, right? So someone might prefer it because it has a higher minimum value, so that the lowest that it can get is still higher than the lowest that brand Y offers. So that might be good. It's also more less variable. It's less spread out compared to brand Y, and therefore is more consistent. So that could be a good reason to prefer brand X. Okay, so we'll give those as potential reasons. Okay, so brand X has a higher minimum battery life and is less variable. Than brand Y. And if we look at brand Y, well, even though brand Y is inconsistent, if I look at the median for brand Y, the median for brand Y is going to be larger, right? And it's going to have a larger maximum, 500 to 509, so potentially, right? And it has a higher center, right? It has a higher median lifetime overall, even though it has some low values here. So what are the value? What's the median of brand X? Let's find that out. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 batteries for brand X. So that means the eighth value, right, is going to be the center here. Okay, so let's look at the eighth value, 0, 1, 2, 3, 4, 5, 6, 7, 8. So here the median is 390 to 399 hours. Whereas if I go to brand Y, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So look for the eighth number, eighth battery, 1, 2, 3, 4, 5, 6, 7, 8. Whereas here, the median for brand Y is 430 to 439 hours. So therefore, it tends to be greater. Okay, so brand Y has a greater median lifetime. And it was 430 to 439 hours. Than brand X. And brand X was, what was it? It was 390 to 399. Okay, so they both have their pros and cons based on the data provided. All right, so let's look at the last problem here. Catherine and Anna suspect that athletes, students who have been on at least one varsity team, typically have a faster reaction time than other students. To test this theory, they give an online reflex test to separate random samples of 33 varsity athletes and 29 other students at their school. Here are parallel box plots and numerical summaries of the data on reaction times in milliseconds for the two groups of students. All right, so we have varsity on the lower box plot. We have the others on the top, and looks like we have a number summary here, right? For the different student type, and so other versus athletes. So here it says there's 29 here, there's 33 athletes there. All right, so are these numerical summaries statistics or parameters? Explain your answer. Okay, so remember, a statistic is a value that describes a characteristic of a sample, right? So this comes from a sample. Parameters come from populations, okay? So is this a population that they studied? No. These are samples that they took, right? They took 29 students. 29 students is not the population of students, right? Or other students, right? And then athletes, 33. There's definitely more than 33 athletes, but they only sampled 33 of them. Okay, so these values are statistics because they are numbers that describe samples. All right, so they describe the samples that were taken for the various groups. So those are statistics. Write a few sentences comparing the distribution of reaction time for the two types of students. All right, so we're going to be specific when we set this up. All right, remember, when you are comparing distributions, you need to use SOCS, okay? Talk about the shape. Compare the shapes. Compare the outliers. Compare the centers. Compare the spreads, right? So you need to use SOCS. So we're going to be comparing with using SOCS here. All right? So shape. Let's look at the athlete group. Okay? The varsity group. If I look at the varsity group, it appears to be skewed to the right. This tail on the right side seems to be longer compared to the tail on the left side. In addition, you can kind of see that because a good chunk of the distribution is on the left compared to on the right. So that means it's skewed right. So now when we look at the other group, this appears to be this appears to have symmetry, right? So it appears to be roughly symmetric, but it does have to have two high outliers. So it's roughly symmetric with two high outliers. So that's something to keep in mind, okay? So the varsity distribution is skewed to the right. Whereas the other so we also want to talk about the context. So I'm going to mention the context here. So here we have the varsity athletes. So I'm going to actually, I'm going to mention that these are the athletes because you want to be specific as possible, especially when you're doing the free response. You want to include context and things like that, okay? As well as the distribution of other students. And also the distribution of what, right? So in this case, the distribution is the distribution of reaction time. So we want to be as specific as possible. So the varsity athletes' distribution of reaction time is skewed to the right, whereas the distribution of reaction time for other students is roughly symmetric with two high outliers. So this is actually talking about my outliers here, right? So we're going to continue talking about the outliers, but it says the varsity distribution has one outlier, whereas the other distribution has two. All right, so now we're going to look at the centers. So the centers for these. Okay, so if I look at the values for the other athletes, the median is 290. Yeah, it seems to be 292, and here this is 261. So it appears that the reaction times for other students, right, who were not athletes, tended to be, the reaction times were slower. They were larger, right, which means that they were actually slower. Okay, so we're going to say the reaction times for students who are not varsity athletes tended to be slower. In this case, we would say that the median was 292 milliseconds. Than for athletes, which was 261 milliseconds. Okay, it's very important that when you provide the response that you are as direct and you are as detailed as possible. I am trying to model what they're looking for, okay? So they're looking for socks. They're looking for all, these details, right? We put the median was 261 milliseconds. Now we're going to look at the spread, right? So the the distribution of reaction times for other students. Now let's look at it. So is it going to be bigger or smaller? It looks like the other is more spread out, right? In fact, we're going to report the interquartile range because remember, we have some skewness to the results, at least for the varsity, right? And the other has also some outliers as well. Even though it's approximately symmetric, but it does have some outliers. We're just going to report the interquartile range here. So here the interquartile range is from here to here. And they tell you the quartiles, so we can calculate that. So the interquartile range of this is 325 minus 255, which is 70. And the interquartile range for the other ones, 236 and 300. So 300 minus 236 is 64. So the spread for the other students is greater than for the athletes, right? So the distribution reaction times for other students is, the distribution reaction times has more variability, right? Interquartile range equals, what was it? We got said was 70. Yeah, so 70 milliseconds. Has more variability than the athletes' distribution. IQR was 64 milliseconds. Okay, that is it for the video, guys. I hope you found this useful. Again, it's good to review all these types of questions so you kind of know what to look for in the your response and in the multiple choice. We went over various topics here, but I hope this was useful to you. And as usual, I will see you in the next one.